So as chemists started formulating these theories, they started to try to figure out what that more information is that we need. So we kind of need a way to quantify particular values for delta S. We know that there's tables in the back of the textbook that have delta H values, and they also have delta S values. The question is, how do we get those values? And at this point, we need a baseline to figure out what those values are. So this is where the third law of thermodynamics comes into play. Excuse me. Thank you. The third law of thermodynamics allows us to come up with all the other values in our particular table. And the third law states that the entropy of a pure crystal at 0 Kelvin is 0. And the change in entropy of a reaction can be calculated from the standard entropy of each substance. So this is going to allow us to calculate a change in entropy for a particular reaction. And we're going to use the same exact method to calculate delta S as we did for delta H. And one of the things that we have to keep in mind is that entropy, or delta S, is an extensive property. And what an extensive property is, it is dependent upon, or depends upon, amount. So the amount of a particular substance we have is going to be dependent upon the overall entropy that we have. And this is consistent with some of the figures that we talked about earlier on in the lecture. Okay? And it's mainly consistent with a lot of energies, right? If we're doing a particular combustion reaction and we need energy, okay, and we need to figure out how much work is done, if I have a 10-gallon gas tank versus a 20-gallon gas tank, I can go farther with that 20-gallon gas tank, because all of these energy calculations we look at will depend on the particular amount. Okay? And appendix at the end of the text lists actual numerical values at 25 degrees Celsius. Typically, those values are listed in joules per mole Kelvin. So the question is, if I have a particular reaction, how will I figure if something is spontaneous or not? And before we go onto that information, we need to be able to calculate the delta S and the delta H of a particular reaction. Okay? So let's look at a way to calculate that. And if we're calculating delta S for a particular reaction, and typically you'll see this delta S naught. I'll say in a minute what that naught symbol means. But if we want to figure out the delta S naught of a reaction, it's going to be the sum of the delta S naught products minus the sum of the delta S naught reactants. And remember what we said, that this is an extensive property, so it's going to depend upon the amount. So typically, when you see these summation signs, you also sometimes in some texts see an N listed in that equation, and this N accounts for the number of moles. And we get that number of moles from the balanced chemical equation. So make sure when you're reading these particular problems and you're doing these calculations that you're given an overall balanced chemical equation. Okay? So we'll go through an example of this. And in our particular example problem, we're going to take NaHCO3, which is a solid. And remember, the phase that you have is completely different, or the entropy and enthalpy values can be completely different depending on the phase that we have. So it's very, very important in these particular chemical reactions that we list the phase. So here we have NaHCO3, which is a solid. Its reaction gives products of Na2CO3 as a solid plus H2O as a liquid plus CO2 as a gas. And when this particular reaction proceeds, it's going to bubble, which gives evidence that that CO2 gas is released. If we want to balance this particular equation, we need to put a coefficient of 2 in front of the NaHCO3. If we look back in the textbook, we can get particular values for delta H naught of formation and for delta S naught. The delta H naught of formation values are going to be listed in kilojoules per mole, and the delta S naught values are listed in joules per mole times Kelvin. Okay? Notice that when you see these values in a table, they have different units. The value for our NaHCO3 is going to be negative 947.0 in terms of kilojoules per mole for our delta H of formation. For the delta S, we're going to have 102, and this is joules per mole Kelvin. I'm just going to go across for each of the three products and list their delta H values. It's going to be negative 1131, negative 285.8, and negative 393.5. All of these units are in kilojoules per mole. The delta S values are going to be 136, 69.9, and 213.6. And these are all in joules per mole Kelvin. Compared to what we were doing last chapter, the math of this stuff is pretty simple, right? So if we want to calculate our delta H naught of formation, it's going to be the sum of the products minus the sum of the reactants. So we're going to have, in terms of our products, we have 1 mole times negative 1131 kilojoules per mole plus 1 mole times negative 285.8 kilojoules per mole plus 1 mole times negative 393.5 kilojoules per mole. This is going to be minus all of our reactants, which is going to be 2 moles times negative 947.0 kilojoules per mole. If we go through and do the math, our delta H naught of formation is going to equal positive 85.1 kilojoules. The same exact process has to be done for the delta S naught, and we use the same formulas, just plug in the different values. And our delta S naught is going to equal positive 215.5, and that's going to be in units of joules per Kelvin.